Hi, this is chapter 8, first slide, physical database design and database infrastructure. We're gonna study definition of terminology, and also we will describe the physical database design process, and then we're gonna choose storage format for attribute, and then we're gonna select appropriate file organization. And also we're gonna describe 3 types of file organization, and then we're gonna describe indexes and their appropriate use, and then we're gonna translate our database model into efficient structure, including the normalization. Also, we're gonna describe problem and techniques for data security, and then we will understand a lot of databases in Sarbanes-Oxley compliance, and then we're gonna describe problems and facility for data recovery, and also we're gonna describe database tuning issues and risk areas where changes can be done to tune the database. And then we're going to understand impact of cloud-based database services on database infrastructure. And then we will describe advantages and disadvantages of cloud-based database infrastructure solutions. So physical database design. The purpose to translate the logical description of data into the technical specifications for storing and retrieving data. Goal: to create a design for storing data that will provide adequate performance and ensure database integrity, security, and recoverability. So, information needed for physical database. Normalized relation include estimate for the range of the number of rows in each table. Definition of each attribute along with the physical specifications such as maximum possible length, description of where and when data are used in various ways, entered, retrieved, deleted, and updated, including typical frequencies of these events. Expectations or requirements for response time and data security, backup, recovery, retention, and integrity. Descriptions of technologies, database management system used for implementing the databases. Much of the input to the physical design comes from output from requirement, analysis, and logical design. Others stem from business security concerns and regulatory compliance, while still others stem from prediction of demands and performance analysis. Critics decisions for physical design. Choosing the storage format called data type for each attribute from the logical data model, giving the database management system guidance regarding how to group attribute from the logical data model into physical records, giving the database management system guidance on how to arrange similarly structured record in secondary memory file organizations, selecting structure including indexes and the overall database architecture for storing and connecting files to make retrieving related data more efficient, preparing strategies for handling queries against the database that will optimize performance. Query optimization. The primary goal of physical database design is data processing efficiency. The organizational load that typically has the primary responsibility for physical database design is called the database administrator. More about database administration in later chapter. Physical design for regulatory compliance. Sarbanes-Oxley Act SOX protect investors by improving accuracy and reliability. Committee of Sponsoring Organizations, cursor of the Threadway Commission, IT infrastructure rivalry, control objectives for information and related technology. Physical database design forms a function for compliance with national and international regulation on financial reporting. Without careful physical design, an organization cannot demonstrate that its data are accurate and well protected. These listed standards, guidelines, and rules focus on corporate governance, risk assessment, and security and controls of data. For full compliance, all data integrity controls must be thoroughly documented and undergo well-documented change control procedures. The key focus of SOX audit is around this area of control: IT change management, logical access to data, IT operation. Three areas of SOX audit. IT change management. Processes by which changes to operational systems and databases are authorized. Logical access to data. Security procedures to prevent unauthorized access. Personnel controls and physical access control. IT operations. Policies and procedures for day-to-day management or infrastructure, applications, and databases. Figure 8-1 Composite Usage Map, Pine Valley Furniture Company. We create usage map by modifying enhance the entity relationship diagram to include information regarding size of entity, example number of instances, as well as frequency of use of these entity. In this way, we come to an understanding of the storage needs as well as the computational demands of the system. Usage analysis should be an ongoing activity. Data volume, here we see an expectation of 3,000 parts subdivided into manufactured and purchased. We also see 150 suppliers, and we see 6,000 associations, each of which describe a particular supplier providing a particular purchase part, referred to in the next slide as a quotation. In essence, you can think of each entity as a table containing that number of rows. Access frequency per hour. The volume and frequency statistics are generated during the system analysis phase of the system development process, when system analysts are studying current and proposed data processing and business activity. The data volume statistics represent the size of business and should be calculated assuming business growth over a period of at least several years. The access frequencies are estimated from the timing of events, transaction volumes, the number of concurrent users, and reporting and query activity. Usage analysis. 14,000 purchase part accessed per hour. To 8,000 suppliers access from these 14,000 purchase part accesses. 7,000 supplier access from these 8,000 suppliers accesses. The access of data from one table may trigger the need for further accesses in other table. Usage analysis include providing a representation of this expected flow of access requests. 7,500 supplier access per hour. 4,000 supplier access from these 7,500 suppliers accesses. 4,000 purchased part accessed from these 4,000 supplier accesses. The flow can go in different direction. In the previous slide, the flow was triggered by access to part and flow through purchase part, supplier association, and finally suppliers. In this slide, we see a flow in the opposite direction, triggered by initial access requests for suppliers. These access requests could be queries which retrieve data or update which manipulate the data. Each of these imposes some demands on computing resources, so this type of modeling helps to express that demands. Date can represent from January 1st for 712 BC to December 31st 9999 AD. Stores, century, year, month, day, hour, minutes, second. Timestamp, like a date, can include fractional seconds and time zones. Blobs, binary large object, can store up to 4 GB, used for photos, sound clips, etc. Selecting a data type involves 4 objectives that will have different relative levels of importance for different applications. Represent all possible values, improve data integrity, support all data manipulations, minimize storage space. Figure 8-2 example of a code lookup table, Fine Valley Furniture Company. Some attributes have a sparse set of value or are so large that given data volumes, considerable storage space will be consumed. A field with a limited number of possible values can be translated into a code that requires less space. A code table would not appear in the conceptual or logical model. The code table is a physical construct to achieve data processing performance improvement, not a set of data with business value. So in this case, you probably would not see the product finish table in which the conception model or the logical design. So you can see in here, C means oak, A means birch, C means oak, B means maple. So maybe there are the repeated value we can use like this: product finish lookup table. Denormalization. In my sim counterintuitive data database, designer would want to denormalize the previous normalized well-structured set of relation. After all, we spend considerable effort toward conceptual modeling, entity relationship or enhanced entity relationship model in order to ensure well-structured logical design. And when faced with fully structured relations, we normalize them in our logical design. Why denormalize now? The answer is performance. When you normalize, you split data into separate tables in order to eliminate or at least reduce data duplication. This helps to ensure data integrity, but it comes at a cost. It is much more computationally efficient to query a single table than to query multiple tables. Therefore, it makes sense to, in a controlled way, back off from perfect normalization. In the next few slides, we will see some example. Transforming normalized relations into non-normalized physical record specification benefit can improve performance speed by reducing number of table lookup. Example, reduce number of necessary join query. Cost, due to data duplication, wasted storage space, data integrity, consistency threat. Figure 8-3, a possible denormalization situation. So one-to-one relationships are good candidates for denormalization, such as this example of student with application. This diagram, we know that not all students have application. How do we know this? The optional one, the application slide of the submit relationship. Therefore, many students may not have an application, so the application date and qualification field of the denormalized relation may not be used. This wasted space, but as mentioned earlier, space is cheap these days. Figure 8-4, a possible denormalization situation. Here is the case of a many-to-many relationship between vendors and item, which result in three tables. Denormalizing combine the item and price quote table into a single table called item quote. Which attribute will wind up being duplicated in this case? The item description. This means that anytime the description changes, the change must be done to all item quote unless you are willing to tolerate inconsistencies in the item description. So, in this case, there is some comprising of data integrity guarantees. Again, we do this for the sake of performance. A query involving two tables is more efficient than a query involving three. Composite usage map can illustrate the demands on the extra table and therefore can be used to justify whether or not denormalization should take place. Denormalization with caution. Denormalization can increase chance of error and inconsistency. Denormalization can reintroduce anomaly. Denormalization can force reprogramming when business rules change. Perhaps other methods could be used to improve performance of joins. Organization of tables in the database, file organization and clustering, proper query design and optimization. Partitioning. Horizontal partitioning, distributing the loads of logical relation using several separate tables. Useful for situations where different users need access to different loads. 3 types: key range partitioning, hash partitioning, or composite partitioning. Vertical partitioning, distributing the columns of a logical relation into several separate physical tables. Useful for situations where different users need access to different columns. The primary key must be repeated in each file. Partitioning pros and cons. Advantage of partitioning. Efficiency. Records used together are grouped together. Local optimization. Each partition can be optimized for performance. Security. Data not relevant to users are segregated. Recovery and update. Smaller files take less backup time. Load balancing. Partition stores on different disks. Reduces contention. Disadvantage of partitioning. Inconsistent access speed, slow retrieval across partitions. Complexity, non-transparent partitioning. Extra space or update time. Duplicate data access from multiple partitions. As with all physical design decisions, partitioning has its advantage and disadvantage. Designing physical database file. Physical file, a named portion of secondary memory allocated for the purpose of storing physical record. Table space, named logical storage unit in which data from multiple table views object can be stored. Table space component, segment a table index or partition. Extend contiguous section of disk space. Data block, smallest unit of storage. We've been talking about relational database structure, involving table, column, and primary and foreign keys, as if this is in fact the way data is actually stored on disk. But it is not. At the operating system level, we are always talking about files. Databases are just one kind of file. The table column key idea is really an abstraction. At a lower implementation level, this database file, like all physical files, are actually constructed via different file format, which will be discussed in the next few slides. File organization. A file organization is a technique for physically arrange the record of a file on secondary storage devices. Typically, file organization includes sequential indexed and hashed, which we will see in the next few slides. Another possibility is something called a heap, but this has no order and is not ideal for quick accesses. Imagine a telephone book where people were in no particular order. You'd potentially have to search through each and every name before finding one you need. The other file organization are designed to bring quick access and or optimize insertion, modification, and removal of data item. With a modern relational database management system, you don't need to design file organization, but you may be allowed to select an organization and its parameter for a table or physical file. Types of file organization: heap, no particular order, sequential, indexed, hashed. Factor for selecting file organization: fast data retrieval and throughput, efficient storage space utilization, protection from failure and data loss, minimizing need for reorganization, accommodating growth, security from unauthorized use. Figure 8-7, comparison of file organization. A. Sequential. In instance, when data is arranged sequentially, you can cut the search space in half each time you look. For example, suppose you wanted to find the flyer. First, we get the middle item, the wrist. Suppose it was Hoosiers. Since flyer come before Hoosiers, you know it has to be in the group before Hoosier. So then, look in the middle of that group. Suppose this item was Devils. At this point, you know it has to be between Devils and Hoosiers. So the speed of accessing a desired record, knowing the primary key in a sequential file is much faster than accessing it in an unordered file, heaps. But sequential file organization always requires data to be sorted. Therefore, such a file must be resorted every time new items are inserted or if any existing items are changed. So the speed of access comes with a significant maintenance cost. Indexed file organization. An indexed file organization, the records are stored either sequentially or non-sequentially, and an index is created that allows the application software to locate individual record. See figure 8-7b, like a card catalog in a library. An index is a table that is used to determine in a file the location of record that satisfies some condition. Each index entry matches the key value with one or more records. An index can point to unique record, a primary key index, such as on product ID, field of product record, or to potentially more than one record. An index that allows each entry to point to more than one record is called a secondary key index. Storage of records sequentially or non-sequentially with an index that allows software to locate individual record. Index, a table or other data structure used to determine in a file the location of record that satisfies some condition. Primary keys are automatically indexed. Other field or combination of field can also be indexed. These are called secondary key or non-unique key. Figure 7-8-7, comparison of file organization. So A, indexed, An advantage of the index file organization over the sequential is that it is easier to insert and delete data because the index is composed of many smaller lists of actual data items seen in the bottom of the tree. Then sorting an individual cluster is much less costly than sorting the whole file. Also, if you keep the individual list small enough, then even if they are unsorted, the search time is not so bad. The trick is indexing and specifically keeping an optimal number of labels within the index. In this case, we see two levels of indexing, below which are the sum list of data items. The index organization in this figure split at the top level into three groups. Any team's name starting with A3F goes in the first group, those with G through P in the second, and those with Q through G in the third. Within each group, there is a second split into three subgroups each. Indexed file organization is often used with attributes that are likely to be frequently used in query. Part of the physical design process involves choosing which columns of the table to index, as we'll see later. B. Hashing. A hashing algorithm is a routine that converts a primary key value into a record address. Although there are several variations of hashed files, in most cases the records are located non-sequentially as dictated by the hashing algorithm. Thus, sequentially data processing is impractical. A physical hashing algorithm uses the technique of dividing each primary key value by a suitable prime number and then using the remainder of the division as the relative storage location. For example, suppose that an organization has a set of approximately 1,000 employee records to be stored on magnetic disk. A suitable prime number would be 997 because it is close to 1,000. Now consider the record for employee ID 12396. When you divide this number by 997, the remainder is 472. Thus, this record is stored at location 432 in the file. Hashing algorithm could potentially map two different primary keys to the same location. If that happens, there will be a list at that location, similar to the list in the indexed file organization described earlier. Clustering. Clustering record is best used when the records are fairly static, as in a data warehouse. When records are frequently added, deleted, and charged, wasted space can arise. It may be difficult to locate related records close to one another after the initial loading of record, which defines the cluster. Clustering is, however, one option. A file designer has now improved the performance of tables that are frequently used together in the same queries and report. So clustering and join indexes are both done for the purpose of optimizing join query. In some relational database, management system, related records from different tables can be stored together in the same disk area, useful for improving performance of join operation. Primary key records of the main table are stored adjacent to associated foreign key records of the dependent table. Example, Oracle has a create cluster command. And also there is useful clustering files, so we can improve performance of several operations. And then the Oracle has several commands like a create cluster. We're gonna see you later. Bye. Take care.